Today we're gonna give a brief presentation of NewRadX, and this is going to be, sorry about that. This is going to be the first presentation of this code, so I hope it will go well. NewRadX is just a thorn, a CarpetX based thorn that provides radiative boundary conditions ready to use with whatever space-time evolution code you want to use. More specifically, I have here the original paper by Miguel Alcubierre, I believe, where they give a very good presentation of the Sommerfeld boundary conditions that we want to implement, which is the following. And yeah, let me start from here. So in a few words, we want to impose that our variables that we are evolving in our code behave as a wave on the outer boundary of our computational grid. This is described by the following formula, where f is our variable, whichever variable it is. It can be the lapse, some other metric component, a scalar field, whatever field you are trying to evolve. Then there are two parameters here. F of 0 is the asymptotic value of your variable. For instance, as it says here, the lapse is typically 1. Other variables might go to 0. Some scalar fields might asymptote to some different variable. In the second part of the right-hand side, instead, we have the proper wave-like solution, u, as a function of r minus vt, where v is the speed of propagation of your wave. So we want to impose this asymptotically on our numerical solutions. In practice, what we do instead, we impose the Sommerfeld boundary conditions, but in a differential form. This is just the taking the proper derivatives of the expression above, and we finally differentiate this expression over here, and basically impose that our right-hand side of our variables behave with this formula over here. Now, because of the way CarpetX works, we cannot implement these boundary conditions as in a way that AMRX would call a boundary condition, simply because the AMRX or equivalently CarpetX boundary conditions are applied on the outer ghost points, outer boundary ghost points, and those cannot be evolved. Namely, if we were to impose that those points evolved following this formula, that would not work because because of the way AMRX manages the outer points. So we need to impose basically this differential Sommerfeld boundary condition on a strip of points that is corresponds to the ghost points, but translated inwards, shifted inwards. Is a strip of points that we call outermost interior points. To identify this, since we need to present a little bit the details, we are using a templated looping function, custom templated looping function called loop outermost interior.
Alex?
Yes?
That font is way too small for me to see that anything.
Sure, sorry about that. Does this work
That's
better?
Much better, yes. Yeah, much better.
Perfect. All right. So yes, we have a custom looping function that loops over the proper strip of points, which again corresponds to the AMRX ghost points shifted inwards by the this would correspond to the AMRX boundary points shifted inwards by a quantity that is equal to the number of ghost zones. So this n ghost zones. But let me show you how we do this in practice. This was just an overview of the principle that we wanted to implement. And this instead is NewRadX. It's a pretty simple thorn. It has only one important source file. This is the header file where I wanted just to show you the NewRadX function that we provide with the thorn. This is called NewRadX apply, and basically takes as a parameters the variable you want to apply your boundary condition to, the corresponding right-hand side of the variable itself, which is the grid function that we are going to modify with NewRadX apply, and three physical parameters that I showed you in the paper before. The asymptotic value var0, v0 is the speed of propagation of the wave, and there's an additional one that I didn't show you before. It's called rad power, and it pertains to the radiative fall off of your solution. We're gonna discuss this in a second. But let's see a little bit closer what the function does. As I said, this implements a finite difference version of the differential Sommerfeld condition above. This is, as I told you before, the function that loops over the outermost interior points. And once it loops over the points, what it does is simply evaluates the radiative right-hand side, which is here in the comment. You can find all in the comments. You can find all the details, and you can check for yourself if you want. But we are trying to implement this formula here, where and impose that the right-hand side of your variable is equal to the spatial derivative of the variable times the speed of propagation of the wave in the proper direction. And we need to evaluate all these terms in this formula, which is what we do here. We evaluate the local wave speeds in all three Cartesian directions. Sorry again for the coffee. Evaluate the spatial derivative of the variable using the three functions that finds the finite difference approximation of the spatial derivatives, and you can find them here. And basically, the functions try to understand on which kind of how far from the boundary itself we are lying, so that it knows what kind of stencil to apply. If it's sufficient, if there's enough points on the right and on the left, it applies a symmetric second order stencil. Otherwise, it uses asymmetric still second order stencils. And once we have the spatial derivatives, we compose everything together. And we basically impose that the right-hand side of our variable is given by the proper formula. Now there's a second piece to NewRadX where we try to subtract a Coulomb-like potential Coulomb-like behavior of our variable at the boundary. Let me go back to the paper just for a second so that we can see first analytically what I'm talking about, and then we'll see the finite difference implementation. So say that your variable doesn't have just a wave-like piece that we just evaluated before, But there's also a Coulomb-like term with a generalized Coulomb factor with a function of time here, h of t. So what we want to do is evaluate this correction to the Sommerfeld radiative boundary condition and subtract it properly from our right hand side. There's obviously an approximation that we need to impose simply because we don't know some terms in the Coulomb-like fall-off, so we are guessing in a way what is the Coulomb-like contribution here. But this is all of these details are well understood. This was the same way that the same estimation that was done in the previous version of NewRad, and we just followed the same logic. Let me go back to the code now. So this is what happens here. If the third parameter of NewRadX supply, that is rad power, is different from 0, or actually greater than 0, because smaller than 0 doesn't make any sense, then we try to evaluate this Coulomb-like correction and subtract it from the right-hand side. To do this, we need to basically shift inwards again by an additional n-ghost zones points that define this displacement variable here. Subtract.
I'm sorry. How is rad power set?
It's a parameter to our function.
Parameter.
Yes.
Oh, okay.
Here.
So, all right. Okay.
Yeah. I told you there were 3 physical parameters. var0 is the asymptotic value at infinity. V0 is the propagation of our wave. The third one is the one that decides basically the power of r with which your function decays at infinity. If this is 0, nothing happens. If this is different from 0, this means we expect a Coulomb-like fall-off asymptotically, and we want to subtract that from our radiative boundary conditions. Right. I think we were here. Okay. So how do we estimate this piece over here, the Coulomb-like piece? We do a little trick here where we go in, we move inwards by a number of points decided by the number of ghost points, and which means now we are selecting a point, an interior point, a physical point that evolves with our whatever physical evolution equation that we are interested in our problem. Subtract the radiative right-hand side that we've computed, and then extrapolate the difference and subtract it here from our right-hand side. This extrapolation is obviously an approximation, but this is what we can do to have a proper to correct our Sommerfeld boundary conditions. Just to be clear, this is the part of the code that it's a little bit trickier to set. So to set the proper radial fall-off exponent, you need somewhat to do a little trial and error in your simulations. Maybe when you're evolving your metric, your spacetime in GR, this is somewhat easy to understand by just computing the expected asymptotic behavior of your variables. Whenever you're evolving something more exotic, you need just to experiment a little bit with different values of this parameter. So this is it from my side. I hope I gave a proper presentation of what's under the hood of this little thorn. I'll leave the floor to Cheng-Hsin, who instead is supposed to show you how you use this NewRadX apply function coupled to your custom evolution code. And yeah, please, Cheng-Hsin.
All right. Thank you, Alex, for the excellent introduction. So let me continue and let me share my screen. So I think as a simple demonstration of how NewRadX is used. So originally I have written a test for NewRadX where I have set up the evolution of a scalar wave in flat space, and then it was separated into a test NewRadX thorn, and so I'll go into a bit of the details about if you have already a evolution thorn, what are the changes you'll need to add in order to apply the boundary conditions. And so for the most part, this is quite similar to the way it was implemented in the original NewRad with using Carpet. And so here, if we take a look at the test NewRadX thorn, which is under spacetime X, just as NewRadX is, and it's really quite a simple thorn. So there's only one source file, but let me take a look at the interface.ccl. So here you'll see that we just include the NewRadX header. And so in the evolution thorn, let's say I have a scalar wave state vector. So u here would be the value of the scalar field itself, and BV would be the time derivative of u. And so we can the way this evolution thorn works is basically that we update the time derivative or the right hand side functions, and this is where we would modify the original evolution thorn with the boundary conditions applied. And let me go back to the schedule. And so we would see that the main part where the evolution is done is in this one right-hand side routine. And so as Alex showed earlier, we would in NewRadX, we would read the values of the variable that we want to apply it to, and update the right-hand side based on the Sommerfeld radiative boundary conditions. And let me take a look at the main routine here. Oh, and I should mention here that in this thorn, I've simply added the apply NewRadX in the right-hand side routine. Whereas in bigger evolution code, you might want to separate it out into a separate routine scheduled after the right-hand side calculation. But let's jump in here. So here, this is all just auxiliary functions. So setting up the initial Gaussian. And let me jump to the right-hand side calculation. All right, so here, this is the main loop that does the right-hand side calculation. Oops, yeah, so this is a main loop that updates the right-hand side. And so we would follow the wave equation. So where the time derivative of the scalar field is the variable v, and v is simply the evolves according to the wave equation. So it's just a flat Laplacian on the u vector, sorry, the u state variable. And right after this right-hand side calculation, I would just add in NewRadX apply. And so in the same way, I would have the information about the grid as input, and I am applying NewRad boundary conditions to the u and v right-hand side. So if you remember the syntax, this is the state variable and its right-hand side, and I would have some asymptotic value and wave propagation speed, and then the power of the Coulomb-like fall-off term. And so basically, once you have the right-hand side calculation in your original evolution code, what you would need to do is to simply schedule or apply the NewRadX boundary conditions right afterwards. And yeah, let me show. So this is originally written as a unit test for NewRadX, but there's a test parameter file where I set up a Gaussian scalar wave that applies NewRad with a power of fall-off. And then if I turn on the silo output, which gives it the grid functions in 3D, I can see a visualization of what's going on. So this is the test parameter file and showing it on the X and Y axis. And here the color bar represents the scale value of the scalar field itself. And so we would initially start from a Gaussian, and let me play the video so if you can see it evolve a little bit. Right, so as we can see that there is some artifacts like already from the boundary here, but
I'm sorry. So you're running this inside a cubical simulation domain?
yes, cubical domain. So I believe
wow, I was imagining you had to this was working with some kind of spherical outer boundary. That's pretty cool.
Yeah, so this domain from -10 to 10, this would be the interior, but as Alex explained, that we would instead of applying the boundary conditions in the ghost points, which are not shown here, in NewRadX, we would shift inwards by the number of ghost points. So now the boundary conditions are applied, I believe, like 3 points inwards. Yeah, and this is why you would see some kind of like artifacts here, which are now the ghost stones in the what effectively acts as the ghost points in.
No, but I mean, that's really great. I mean, you're significantly off center, and this is a cubical grid. I mean,
yeah, and I just wanted to mention that there's still a little bit of some reflection coming back from the shifted inwards boundary, but most of the reflections are eliminated.
wow.
Yeah, and so hopefully this is a good demonstration of what NewRadX does and how it differs from the old evolution thorn. Sorry, the old NewRadX, NewRadX thorn. Yeah, and yeah, I'll end my presentation here, and I'll invite all of you if you have any questions or comments, or if there's something that's not clear and we could clarify,